All right. Our final talk is Dr. Tyler Morgan Wall, who is a research staff member at IDA and is a developer of the software library skpr?
Skipper, yeah.
Skipper. Okay. A package developed at IDA for optimal design generation and power evaluation in R. He's also the author of several other R packages for data visualization, mapping, and cartography. Oh, I didn't hit a button. Sorry about that.
Nope. All right. Thank you for the introduction. Yes, I'm Tyler Morgan Wall. I am a research staff member here at IDA, developer of the Skipper package. And today I'm going to be talking to you about a simulation study we did that compared the SNR approximation to a Monte Carlo study to see how accurate it is. So we're going to talk about that and then introduce some software tools that we've produced and released to the community to kind of help with this process. So to give you a little timeline for background for why we're giving this talk, or why I'm giving this talk, 10 years ago, IDA released a paper that gave some recommendations on what to do when you're calculating power, when you have a probabilistic or binary response. In particular, at the time, we had a lot of programs that we needed to calculate power for in order to support those test programs, and those programs had responses that were probabilities. So we came up with this paper that had a few recommendations on different methods. The first of which was Monte Carlo, run a Monte Carlo simulation. That's the gold standard. But the second of which, because Monte Carlo wasn't supported out of the box and let's say JMP or Staties or other software tools, we also gave this recommendation to use what's called the SNR approximation, which allowed you to use the standard custom design power interfaces with these software tools and still get an answer for power for these types of designs. So the next year, I joined IDA. 2015, then 2017, we released the Skipper package, which brought optimal design generation and power, Monte Carlo power evaluation to R. We presented on that at DataWorks 2018. 2021, fast forward a few years, we finally got through the peer review process at the Journal of Statistical Software, and that software was published. That was sort of the 1.0 release of Skipper as a mature software package. And last year, I taught a mini tutorial here at DataWorks 2023 on how to do optimal design generation and power evaluation. It looks like there's some timings going on. Just a second. Let me just turn off timings. And here we go. Okay. And those materials are actually available. There's a 2-hour video of it available on IDA's YouTube page, which we have a YouTube page, surprise. But also we have on the DataWorks 2023 website, there's a lot of the course materials all available. So there's a 3-part course that you can take that goes into everything you need to know to do get started in R with Skipper. So that brings us to 2024, where we want to look back and see with the developments in tooling to support Monte Carlo evaluations in the last decade, is it still worthwhile to use this SNR approximation method, or should we really just migrate to Monte Carlo? Is the SNR approximation still worthwhile? Is the trade-off between computational and analyst efficiency still worth it when you compare it to the gold standard Monte Carlo method? And the short answer, which you can decide for yourself when you see the data, is no, it's not. But there's some pretty convincing results, I think, that demonstrate that. So don't take my word. Look at it yourself. And if not, can we bring that easy power calculation we've provided in the Skipper package to JMP so that analysts who, let's say, are in organizations that they either don't have the IT capabilities to install R because lots of places are constrained, they can't use these sort of open source languages, or they're already just trained up on JMP. And why do you want to train up on two different things? You are an expert in JMP, you're going to continue using JMP. So we want to provide this Monte Carlo capability, this easy Monte Carlo, because you can do Monte Carlo, but something that's basically point and click, like the custom design interface in JMP. So the overall outline is I'm first going to just motivate like what makes it difficult to calculate power when you have these binary responses. Then I'm going to give a quick overview of what the SNR approximation method actually is and what it's doing and how it sort of works around the difficulties for binomial responses. Then a quick introduction, just basically telling you what the Monte Carlo method is and why it's so good and why it's so well suited for power analyses. Then I'm going to show you this very short analysis, but again, I think pretty convincing, showing why the SNR approximation is not a good method in 2024. And then talk a little bit about skpr and skpr-JMP. So background, why is it difficult to compute power when your response is a probability? We often deal with probabilities in terms of programs. We have, oftentimes, we have response variables that are stated in terms of probability or thresholds that are, probability of detect of X amount, probability of identify of Y amount. And we want to use these as responses because in the end, oftentimes we have to test against these things exactly. That's how we decide if the system is good enough. So here I've shown a little toy example of a test where we have a anti-ship cruise missile being launched against some sort of vessel. That vessel is launching an interceptor to try to intercept that missile. And what we want to characterize is the probability of intercept. So here we're launching 100 missiles. Either we have, or interceptors, either we have a ton of money, or this more likely, this is being done in M&S. So we're trying to intercept these, and we want to characterize what is the performance of the interceptor. So let's say the interceptor performs very well. So it has a very high probability of intercept, 0.99, 99% of the time it intercepts the anti-ship cruise missile. In this case, you can see that the width of the confidence interval, so the point estimate is 0.99, but the width of the confidence interval, you can think of that as sort of the noise in this estimate, ranges from 0.94 to 0.99. So it's a width of 0.05. So what happens when the performance of this interceptor is much worse, let's say only 50-50. What happens to that confidence interval? And these are all binomial exact tests, so this is how we're coming up with these. We can see here it grows by a factor of 4. So purely due to the performance of the system under test itself, our uncertainty has grown by a factor of 4. And if you've done a power analysis, you know that the way we tend to frame coming up with power analyses for our programs is in terms of signal to noise ratios, which is to say we assume some one signal to noise ratio across our space that we're looking to detect. So we're trying to detect some sort of signal within some sort of noise. For linear models, the assumption is this noise is constant. But for binomial responses, what happens is this variance changes in this parabola, basically where it goes to 0 at 0 probability and 0 at 1 probability and has a peak at 0.5. And this violates, so for linear regression, this plot looks like a flat horizontal line. So you can see why this would violate that assumption behind linear regression is this changes dramatically, especially if you're near the edges. So how we get around for this when we're analyzing the data is we don't use linear regression. We fit a generalized linear model or do a logistic regression. Usually there are lots of different methods, but that's the most common. The downside to logistic regression is there's no closed form solution for power like there is for linear regression. So here I will show you an example of what the idea behind the SNR approximation is. So what you're seeing here is that same parabola that represents the variance values. Here we have an actual design where we've calculated what the variance is at the various design points. So this is 2 categorical factors, each with 3 levels. So we can actually calculate what the variance values are. Those are the black dots corresponding with the black lines to the variance values on the y-axis. So we see here when we have a relatively small effect size, so that effect size of 0.05 that we're trying to detect, we actually don't see much variation in that variance. It ranges from 0.2 to 0.15, so it changes by a factor of 33% depending on what test point you're testing. But this is a relatively small spread, so what the SNR approximation is doing is just saying, well, let's ignore that small change and we're going to be overestimating some test points, underestimating some other ones, but we're just going to treat it like a linear model and then use our standard power calculation tools, just assuming it's linear. So you can see why this might start to fail. Here, we just have increased the effect size by, I don't know how easy it is to see there, but you can see that the blue marks in the bottom that shows what the effect size is, to 0.7 to 0.9. So an effect size of 0.2, which is to say you're looking for a difference of probability of 20%, which is very common, especially in the DoD test community. And here you can see now our variance changes by a factor of 5, depending on the test points. So you can see that eventually there is going to be some case where this SNR approximation is going to fail. And what we want to determine in this study is where it fails and how badly it fails. So additionally, and we want to determine if there are any cases that we still can use the SNR approximation because it is so easy and simple for an analyst to implement, that it would be nice if we could make some recommendations on, well, if you have this type of model or this type of design, you can still use it. So what are we comparing it to? We're comparing it to Monte Carlo power simulations, which is to say Monte Carlo is just a type of analysis where you're using random numbers to solve a problem. In this case, you're actually simulating running the experiment with an assumed effect size, and then just using the same analytical tools you plan on using in your analysis to then determine if it's significant. And you repeat that process over and over and over again, and just simply count the number of times the tools that you're planning on using in your final analysis are able to actually detect that effect. And that link between the power analysis and your actual analysis gives a very strong analytical basis for the accuracy of these numbers, because they're being generated using the tools you will end up using for your actual analysis. So by counting these up, so if let's say you detect that out of 1,000 simulations, 900 of them you saw were the significant effect that you set up in the simulation existed, then that would mean you have 90% power. The only downside to Monte Carlo, as far as I'm concerned, is the fact that there is a little bit of noise because it is a stochastic process. It relies on this random sampling. So because of that, you have to do a lot of samples in order to get this to converge. However, unlike many test beds and simulation sort of programs where we have to deal with very expensive, time-consuming manpower and consuming simulation test beds, in this case, these simulations run very quickly. Fractions of a second each. You can run thousands of these in under a minute on a standard consumer laptop released in the last decade. This is not something that requires any new sort of computational or manpower resources. If you can run JMP or if you can run R, you can do these types of analyses. So now we get to the actual meat, which is about 3 slides in this presentation of the study. It really, it's really apparent what I'll show you. But we want to assess the accuracy and reliability of the SNR approximation. So by accuracy, I mean how is it biased or not. So we're going to look at seeing how it's biased, comparing it to Monte Carlo, and going to see how wide that bias is. So you could conceive of a scenario where you might have a very tight bias that's always, let's say, under-predicting by, let's say, 0.1 power. And in that case, you might make the recommendation that, okay, while we're not, we might have, it might be inaccurate and biased, but it's always, it's pretty tightly bound. So in that case, you might say, okay, well, why don't you just add 0.1 to all your power estimates? So this is what we're trying to characterize. And we also want to look at the reliability of it, which in this, I'm using that term here to see where and when it fails. So does it consistently fail when you, let's say, have different designs with different characteristics, which I've listed out here. So the SNR approximation is just a system, a tool that we can assess like any other tool we assess in the test community. We have a figure that we're trying to, response that we're trying to look at and characterize, which is to say bias. We have a bunch of input factors that we want to characterize how it changes the bias. So in this case, I have the number of runs. I have the effect size, whether it's narrow, whether it's wide, whether it's centered, whether it's offset. The type of design factors that are included, categorical, continuous, the number of levels in that categorical factor, type 1 error, optimality, and in this case, we're also looking at whether main effects or main effects plus interactions has an effect. And a lot of these were included because these are things that we saw as we were comparing these designs in the real world were having an effect on the bias. So yes, this is a DOE to look at a tool used for DOE. So ideally, if the SNR approximation had zero bias, this is what this plot would look like. So this is a histogram of the bias value. So what we did is we took each of those 480 designs, we calculated the power for each one of the factors, and then we one by one compared them, a one-to-one to the Monte Carlo versus the SNR approximation to determine what the bias is. So this is a histogram of all of those different bias values. And to the right, that is when the SNR approximation would be over predicting power. So when, which would increase your risk of under testing. So you think you have more power than you do, so you don't size the test to the level that you would if you had the accurate power calculation. To the left, we have points on that side represent under predictions of power, which is to say that the SNR approximation would be saying you have less power than you actually do. So you would be increasing the risk that you would then waste resources and money and time to execute a test that you did not need to do. So all of that leading up to really the primary results of this, which is this plot. It's a little harder to see, but you can kind of make it out. You can see that we have a slight bias towards under predicting or towards increasing the risk of under testing, which is to say the SNR approximation tends to over predict power. However, note the width of this distribution. When I talk about accuracy, we have over predictions with the SNR approximation of up to 0.8. So this is the equivalent of saying thinking you have 90% power when you actually have 10%. So conducting a meaningless test when you think you're real sure of these results. And on the left side, we also have cases where you have under predictions of power of over 0.5. So which is to say, you think you have 30% power when you actually have 80%. You could have done your test at with 80% power with a fraction of the resources. So that's the sort of bounding case. But we can also see this varies a lot across the whole space. This is not just the case where it's over or under predicting power, even though it does in general tend to over predict your power. We can see in 25% of the cases we looked at here, it actually under predicted power. So using Monte Carlo is not always going to increase the size. We never like to increase the size of our test, but we can see that when you do an accurate assessment, sometimes you actually get some money back, you get some resources back, you get a smaller test. And that's because what Monte Carlo is doing is just giving you the accurate result. And that's truly what we're trying to do, is just get as much of an accurate result to the decision makers that are using power to assess the risk of these test programs and make a judgment based on what the test size should be based on that. So to the second question, reliability, are there any corner cases where we can say that the SNR approximation can still be used? Here is a factor level analysis. So we analyzed all of this data based on all of these different factors to see if there were any things that do or don't influence the bias in any which way. Here we see that we see a lot of effects, some which are negative, some which are positive. But what I want to note is look at the interaction term. It's at the very bottom. That has the largest negative bias, whereas the interactions and largest, when you combine interactions and you have a large offset probability, you have an extremely positive bias. And there is actually a bunch of examples of dramatic sign changes depending on the exact specifics of your model, which means that this tool is going to, the accuracy of this tool is really going to depend on the exact specifics of your design, which is to say that you don't know if the SNR approximation is accurate unless you conduct a Monte Carlo analysis, which is to say, just do the Monte Carlo analysis. So the overall takeaway is it is an unreliable method, and now it does have a peak sort of around 0. So you might get lucky, and it might end up working out where it comes out to a 0 bias. But in general, really, this is not a good method for when you have multi-million-dollar test programs with effectiveness that impacts people's lives on the line. So now that we've covered that and say, okay, don't use the SNR approximation, what other tools can we use? Because we just threw out one of these, well, I just recommended throwing out one of these tools that is used widely throughout the test community. So, of course, being the author of the R package skpr and being a prodigious R developer, I would highly recommend using it. I've worked on it for the last, almost 6-7 years here at IDA. It's a great tool for if you work in R. It's been marked as a core DOE package by the CRAN. It's published. It's been externally peer-reviewed. It's used throughout the test community. Multiple OTAs have used it. But in addition to that, it's also used outside in academia. So it's been used by multiple institutions for conducting their own research studies, and it's been cited several times, as well as GlaxoSmithKline has used it to support some of their testing in the pharmaceutical industry. So it's been used throughout multiple communities, and you can check out the paper if you want to learn more in depth of what it's doing. We also have those resources I talked about in terms of if you want to check out the class I taught last year. And it's free and open source. So you can just download it. If you can run R, you can run this tool. Here's just some examples. I've had lots of people come up to me at DataWorks to tell me what programs they've used it on. It's been used throughout cross domains, air, space, land. It's a general DOE tool, so it can support any kind of test program. Now, the issue I think for a lot of people is they don't know R and they don't want to learn R because they have enough stuff on their plate. Understandable. So skpr also comes with a nice GUI interface. So graphical user interface, point and click. You can do design generation, Monte Carlo power evaluation for all GLM, Poisson, exponential, split plot designs. You can add, previous versions of skpr had a limitation on the number of factors you could analyze based on, I had to hard code it in. I removed that limitation this past year, so really you can support any number of factors in your design now. It also provides a nice little, so you can analyze using Monte Carlo, also the survival analysis, so power for survival analysis. And it also provides a great little pane where you can actually look at the code that's been generated, so you can then copy and paste that code and have a reproducible script to come up with that power analysis. That all being said, and one final thing is that, so on testscience.org, we've actually uploaded this to the website, so you can actually do this on your phone. So you can whip out testscience.org right now and pull up skpr on your phone, and in a meeting you can say, let me rerun that DOE, and then have an answer in 2 minutes, and be like, actually, I think it's fine. Really, there are very few barriers, I think, to using this. However, I know some people, you're not going to trust open source software. You're not going to trust a random website that might have been, cyber security experts are like, no, I'm not going to do that. So we have now implemented this, a subset of skpr's capabilities in JMP as an add-in, skprJMP. This uses a lot of jumps, so it's written in JMP scripting language, but provides this really nice GUI interface that is really just exactly what you need if you wanted to do a probabilistic power for a binomial response. You have a low and high probability range. You can also set your anticipated coefficients manually if you're doing something more complicated. You have this nice, if you're used JMP before, you have this nice model building interface that it makes it really easy to figure out, to add in a model. And then you just put in your number of simulations, set a few other options, and then hit run. And the entire thing is this one pane. So I don't know how much more straightforward that can get. But I think it's actually a little more straightforward than the SNR approximation, because most of those require an external Excel tool or other table to actually compute what the SNR is. So this is entirely in JMP, so you never have to leave JMP, which I think will be a real benefit to some people. And here you can see that it just outputs a table of effect and parameter powers. I am going to be at the poster session after this with a live demo of both skpr and skprJMP. I would be happy to, especially if you have lots of questions on the software, that would be a really good place to come and talk to me because I can talk for a while. So find me there. I'll be up right next to the bar. So makes for a good conversation. So the overall conclusions, I would not recommend the use of the SNR approximation. If at all, you can do a Monte Carlo. It really does provide not a great estimate for power, and we try to decrease the amount of controllable risk in our test programs, and this is one area where really you control the risk as the analyst because it's an analytical method, so let's use the most accurate one possible. For accurate power assessments, use Monte Carlo methods. This is just in general. There's a lot of places, if you're doing a Poisson or exponential regression, those two are things where you can't necessarily or don't always have the ability to do closed form solutions. So if you use R, use the skpr package. I recommend it. It's great for doing the sort of analysis you do in JMP, but in R. And if you use JMP, check out skprJMP. It's where we just released it last month, so might still have some growing pains, might still have some bugs. We'd definitely like to hear people's feedback and see what they might want to add if they want, if they do want exponential or Poisson regression or what they would really want to see in that, because we can look into adding that. So thank you so much, and I hope this was useful.
For systems in which the signal-noise ratio, or SNR, is applicable, there typically seem to be readily available methods to choose or add points to improve power. While the Monte Carlo methods are accurate at saying what is your power with this design, are there ways to in skpr or skprJMP to choose a design with power in mind?
So both, so skpr, what it primarily deals with, so it generates optimal designs. So that is what, there are other cases where you might want to, like I think, where you might want to have some other sort of iterative approach for adding points to a design. In this case, you do the design generation piece separately from the power evaluation piece. So yeah, those two processes, design construction and power evaluation, are separate. There are, one of my examples for how you'd implement a custom optimality criteria, even though it wouldn't be very efficient, is you could technically, there is an option to write your own function that, let's say, you look at all of your different power values after assessing your power or calculating your power, and then you basically do an exchange based on, what increases your power, whatever criteria you've developed for, what you're trying to maximize. That wouldn't be very efficient, but you can do that because there is a sort of like, okay, you want a custom optimal design based on some criteria that you have. But in general, our optimal design generation features are all like standard DI, alias A, A, B, C, D, E, F, G. So those criteria is why we generate the designs.
Thank you.
Yep. Hey, Tom.
Tyler, thank you. This is great. It's painful to do Monte Carlo simulation for power and JMP, and I think you've removed the pain. And I did want to comment on the question back here. You can do weighting on optimal designs in JMP. So yeah. One of the examples I do frequently show is a lot of people, when you make a typical optimal design, the power for the quadratics are low. And so if you go into optimal, you can increase the weight on those, yeah. and make a trade-off. And you can make multiple designs and see, how much am I willing to give up on my power, on my interactions, to increase the power on my quadratic. So I think it is great that people want to try to do that.
Yep.
There's no more questions. There is a poster.
There is a poster.
Well, a
Yeah.
live demo with the poster.
Yeah, I had to do both because I don't think Ida knew how to do just like, I'm just going to be at a screen. How do you publish that? So yeah, there's a poster. But yeah, check it out. You can poke and prod at it, and happy to see if you break.